Hello, welcome to our presentation here on the WCTF 2020 challenge, Spaceless Spacing. This was a challenge created by Shellfish. So we aren't given much information in terms of what's going on in this challenge from the challenge description. We are told basically that we can connect to some service at some IP and port. And that's really all we know. We don't even know necessarily what protocol it's speaking or have any kind of idea on what's going to happen once we connect to that. But of course, the most important thing to do when getting a challenge like this is to first start by connecting to that port. The goal is kind of to figure out what is the challenge speaking. So we can see here from this example of trying to connect up to the challenge that when we netcat into the service and we just pipe it through hex dump, because spoiler alert, I know that the response is going to be binary, but if you didn't know that, you would get back random characters. But regardless, once we start piping it through hex dump and we just kind of send it some random data, we can see all of this binary data comes back to us. Now this might be maybe a little intimidating at first, but we kind of have no clue what this all sort of means. What is it? So the simplest answer to that, in order to figure that out, is, well, let's just Google for it. Maybe this is some known binary protocol that always kind of starts with this sequence at the start, and that if we Google for it, maybe we'll find other people talking about it. So what does Google reveal? Well, it turns out that suspicion is exactly right. If we Google for this binary data, Google reveals that this is the beginning of an HTTP 2.0 header frame. So you may have heard of HTTP in the past. In general, a lot of servers use HTTP 1.1, which is a text protocol. But HTTP 2.0 starts using a binary protocol. And we'll kind of see as we get further into this presentation what that's all about. Okay, so now that we know, or at least based off of our research, we've kind of concluded that we're likely speaking HTTP 2.0, how do we actually talk to it? So in most web challenges, you can talk to the challenge by just running curl at it. But curl, in this case, gives us this weird message that says received HTTP 0.9 when not allowed. It's not exactly clear kind of what that means, but you can, of course, Google around for that message, figure out why are we getting this response. It's not just completely giving us nothing or like error failed, it's giving us this like kind of specific message that our HTTP isn't allowed or something. And if you Google, you can actually find that there's a flag that you can pass to curl, which is HTTP 2. And since we've Googled and found that our service is speaking probably HTTP 2 based off of what we've kind of discovered so far, we might try this flag and see if that fixes it. Of course, as we can see in this slide, that does not fix it. Unfortunately, running HTTP 2 with the --HTTP 2 flag here doesn't exactly work for us, but no worries. If we keep reading documentation on some flags to curl, we will stumble upon another flag, which is HTTP 2 prior knowledge. So not many web challenges communicate with HTTP 2. It's kind of relatively new. And it's kind of useful now to be able to understand, well, okay, so we have these new HTTP 2 services. How do we speak to them with our familiar tools? And doing some basic research on what that looks like, we've kind of come to the conclusion that there's this HTTP 2 prior knowledge flag that if upon reading about it, it basically says we're kind of asserting that we know that the server is speaking HTTP 2. HTTP 2 has other modes of working where it can basically upgrade a HTTP like 1.1 connection into an HTTP 2 connection, and then you wouldn't need this prior knowledge thing. But it turns out that the service that we're talking to only speaks HTTP 2. It will not respond to our HTTP 1 requests. So that's kind of why this flag is required upon kind of looking around for that. And we kind of see that once we successfully are communicating with the challenge, that it sends us back this user bin env Python as well as some Python code. I've kind of abbreviated here because it's like 30 or so lines of Python. It doesn't fit well on a slide. But it gives us kind of the challenge information. It gives us what the service is running. So this is, it's going to make the challenge a bit more straightforward. And this is how we get to know what it's doing. So it defines basically two routes. The first one was the route that is for the index that just gives us what the source code is that's running, not exactly relevant. But the second route is kind of the one that's most important for this challenge. It is this check secret route. And upon inspecting it, we can see some various things. If you look into this kind of for loop, we can see that we're iterating over both the secret we pass it as well as what the kind of globally defined secret is, presumably the flag. And we can see it's doing this kind of like strange string compare thing. So we can see that if there's a space, it'll just kind of like ignore whether or not it's correct. If the two characters aren't matching at some point in this string comparison, it'll just tell us we're incorrect. If neither of those are true, it'll actually do a super small sleep. It'll sleep for Planck time, which is basically the smallest unit of time with laws of physics. And then after we do this string comparison, we check again if there's a space at all in what we passed it, and if there was, it's incorrect. Otherwise, it gives us correct. So this is basically a custom string compare function. And in general, whenever you see a custom string compare function, especially one that maybe does some like time.sleep, a good thing to think about is potentially some sort of timing side channel. Another thing, though, that we notice is that at the very start, we can see that it's comparing the length of our secret that we're trying to guess versus the correct secret. And if the lengths are not correct, it'll tell us this spaceless spacing, I guess some sort of reference back to the challenge title. Okay, so let's make sure we know how to interact with this challenge, that we've kind of got a good assessment of what the source code is. Now, so if we used our HTTP2 prior knowledge flag with curl and we append /test to the end, we will get back this response spaceless spacing. So presumably a length of 4 for the number of characters in test is not the correct flag size. So we can pretty clearly see that we can actually just kind of brute force the flag size, right? There's not going to be that many options of how long the flag is. So if we just run through and send an increasing number of characters, we can see in this case that once we do A, B, C, D, E, F, G, H, I, J, 10 characters, we get back this incorrect message. So we've kind of already learned now that the flag is 10 characters long. Okay, so what else is going on with this challenge? So we said that there is this custom string compare. And there's this super small sleep, basically as small of a sleep as you possibly can get. But the thing to realize with this sleep that is as small as you can possibly get is that this has to perform a syscall in order for this sleep to go through. So there's going to be some reasonably larger time that it takes in order for this sleep to carry through. It's going to have to basically context switch our application out into the kernel and eventually context switch back in, which is going to take more than just a Planck time worth of time. It's going to take maybe on the order of a nanosecond. Okay, so what this means for us now is we need to figure out kind of what's going on with HTTP 2.0. In fact, if we look back at this challenge again, the thing to note is that in the past, we have this challenge running on a remote server. And even though this sleep isn't just one Planck time worth of time, it's going to be maybe more of like a nanosecond or so. Due to the fact that this challenge is running on a remote server, it's not clear how we are going to measure the time difference. So we can see, for instance, so we know that there's 10 characters in this flag, and that we can provide a bunch of spaces to basically kind of ignore everything that we're not interested in kind of guessing. But suppose we wanted to send A followed by 9 spaces versus B followed by 9 spaces. And suppose that A was the correct answer. In that case, A would actually do a sleep for on the order of about a nanosecond, whereas B would not. And this is kind of provides the opportunity for a timing side channel, measuring that difference. But the issue is that since we're on a remote server, how do we measure a 1 nanosecond time difference? In the past, especially in the context of web, but really in the context of most CTF challenges, a nanosecond worth of time that we need to measure isn't possible. Just the variance in the network of your packets being sent at just slightly different times is going to be much more than 1 nanosecond. You aren't going to be able to measure the difference of 1 nanosecond. Certainly no CTF challenge I've seen in the past has any even remote capability to be able to measure such a very small difference in time. 1 nanosecond is extremely fast. Even if it's not a Planck time worth of time, it's still extremely fast. Network variance is going to way dominate this amount of time, and you're not going to be able to measure it. And this has kind of been kind of a thing that prevents timing side channels against remote targets. Of course, if you're going to sleep for like 2 seconds or a second or a much larger amount of time, you can begin to measure that. But this is a nanosecond. This is extremely fast. You can't measure that over a remote network, except you can. Okay, so the thing to note, of course, is that this challenge is running HTTP 2.0. So maybe you're not super familiar with this protocol. As I said, it's relatively new, and most people are familiar with HTTP 1.1. It's kind of the more common, especially in the context of web CTF challenges. I have yet to personally play in a CTF challenge that uses HTTP 2.0. So I think it's kind of great that we have this challenge that uses more modern technologies and kind of explores what's going on there. But anyways, we can see it's kind of the familiar stack of IP, TCP, potentially TLS. But we can see for HTTP 2.0, there's this binary framing. And with this binary framing, it allows us to, I guess the first thing to note is with binary framing, it kind of makes sense that we're getting binary responses back rather than the familiar text, like new line delimited sort of thing. So let's see kind of what's going on with HTTP 2.0. It's kind of important to understand how this works in order to understand this challenge. And I think it's great to learn how it works. Okay, so we can see here that we have these different frames. And our header goes into one frame, our data goes into a different frame. That's kind of the high-level overview. Maybe that's kind of similar-ish to HTTP 1.1. Maybe not exactly sure what's going on there. But the more important thing, especially in the context of this challenge, is the fact that HTTP 2.0 has this concept of different streams going along the same TCP connection. So just using one TCP connection, you can actually be simultaneously sending multiple HTTP requests over HTTP 2.0. You don't have to start up 2 TCP connections in order to simultaneously make 2 HTTP requests. Instead, just one TCP connection will be more than enough room for us to do our 2 HTTP requests. And this is a big deal. And this is a big deal because what are we trying to do with this challenge? What we're trying to do, and what I just previously said a few minutes ago, is that we're trying, ideally, it would be great if we could make it so that our 2 requests of what we are trying to measure hits this endpoint at exactly the same time. If we can make it so it hits it at exactly the same time, very consistently, then we're back basically to the idea of doing a timing attack against a local host target. And doing a timing attack against a local host target, there's all sorts of CTF challenges that explore this idea. It's a very doable thing. So what this means for us, and what we can find if we continue to maybe look a little bit about this, is that there was a paper published this year in a top-tier security conference, USNIX, titled Timeless Timing Attacks, Exploiting Concurrency to Leak Secrets Over Remote Connections, the emphasis being on remote connections. So this was released in August of this year, so a very recent paper. And this paper kind of brings forth this new idea of how we can leverage things like HTTP 2.0 to do what they call a timeless timing attack, which maybe you're kind of thinking spaceless spacing. There's kind of a reference there. So this is definitely the right track. So we have this timeless timing attack. And what this timeless timing attack does is it basically means, actually if I go back to looking at this, it basically means that we can send two simultaneous HTTP requests at the same time over one TCP connection. So doing it over one TCP connection means we're not going to lose out on network variance and make this impossible to measure. Over one TCP connection, both requests will arrive at the target at the same time if we structure our request correctly, interleaving them basically so they arrive at the same time. And then this timeless timing part basically is a reference to the idea that now we don't even need to measure how long it takes. So if we're thinking about if it's correct, right, we're going to have this time sleep, we're going to sleep for basically a nanosecond. We don't even have to measure the fact that we took a nanosecond longer, maybe we took plus or minus 10% on that or 20%. We don't have to deal with this variance issue so much. Instead, what we can do is we can just see which one was quicker. And which one was quicker, if we look at how this works, the response that comes back, or the one that doesn't sleep, is going to send back its response first over this TCP connection. So we can basically send two HTTP requests simultaneously over our HTTP 2.0 connection. And then one of them is going to sleep for a nanosecond, the other one won't. The one that didn't sleep for a nanosecond will come back to us before the one that did sleep. And that we can measure. We can measure which request came back first. So if we look again at this paper, Timeless Timing Attacks, this is exactly the idea of the paper. That we can take these two simultaneous requests and just measure which request came back first most often. So you might do this, say, 20 times to maybe deal with a little bit of variance, even though it's 1 nanosecond. You could have weird stuff going on that kind of determines, maybe slows one of the connections down, maybe one of them gets preempted, whatever. So you maybe want to do like 20, 30, however many attempts to make sure you're right. But on average, and very frequently, the one that slept for 1 nanosecond is going to come back second. And this is important. We can measure this. This is exactly what this challenge is trying to explore. It's trying to explore this USNIX paper that was released this year that kind of opens up a whole new world of what they call timeless timing attacks. It opens up a whole new world of now being able to do timing attacks against remote targets. And these are like serious remote targets, right? This is like a fundamental new relevant thing within HTTP 2.0. Any application now that's using HTTP 2.0 and has some sort of timing issue over sensitive data. So of course this is like artificially introduced for the purpose of this challenge, because the goal is really to learn here. We're trying to really explore this concept of this new concept here. We can see that basically now any new HTTP 2.0 target that has some sort of even small timing difference over sensitive data, suddenly everything's changed. Suddenly with HTTP 2.0, we can actually measure that. We're not restricted by network variance anymore. We can actually just see which request comes back first. And since it's going over the same TCP connection, the packets are going, by TCP, it's guaranteed to arrive in order, at least when it gives you the response back. And so now we can basically do these remote attacks. So in the past, you've always been able to do kind of local timing attacks. You can kind of measure on the hardware without having to deal with network variance. But now in these domains where you could do a local timing attack, you can suddenly do a remote timing attack if the challenge or if the target is using HTTP 2.0. This is amazing. This is a whole new world for timing attacks against remote targets. And HTTP 2.0, it's a massive thing. There's lots of websites these days now that are actually using HTTP 2.0. Even if most CTF challenges that we kind of work on over the last couple of years aren't really using HTTP 2.0, a lot of websites out there are using HTTP 2.0 or have the capability to do it. And this means now we can do a timing attack against a remote target. This is insane. Okay, so as we said, this is kind of the multiplexing idea. Okay, so what do we do? What's the solution? I think we've kind of talked about it a bit, but let's just kind of reiterate. Okay, so if we can make multiple simultaneous requests for the following, so some known wrong character. Let's assume that we know that there's not a star in the flag. And then we can, at the same time, send a request for some guessed character, say A. And we can measure which one comes back first versus which one comes back second most often. So say you do this 20 times, and maybe you get a split of 10 and 10. If you get a split of 10 and 10 for when these come back, what that means is that they're basically the same. They take about the same amount of time. So that would probably we'd be able to infer then that A is incorrect. Okay, well now let's do it for B. Let's say we get like 9 or like 8 and 12 back. Well, maybe the one that took 8 is quicker, maybe not. But maybe we do C next, okay? And C, let's say it gives us 19 and 1. That the wrong character, the star character, the response comes back first 19 times. Well, that is very suspicious. That would imply to us that when we do C, that we're probably sleeping for a nanosecond, that we're actually going to be able to measure this difference. Okay, so now let's see what the attack looks like. We've kind of gone through this presentation. We've kind of talked about HTTP 2.0. Let's see the attack in action. Okay. So I have a remote running AWS instance on this left terminal, and I've got an exploit script that is in the released material, or at least it'll be released after the CTF, that basically allows you to deploy the challenge as well as deploy the exploit for the challenge. Okay, so if we run this now, we can see that we're making requests. We're currently brute forcing the length. So we can see that we just brute forced the length and we got that the length was 10. We kind of already discussed how we can do that. And now what we're doing is you can kind of see it's going super fast, but we're testing this first character and then the rest we have a bunch of spaces. Okay, we've got our first one. So as we were talking about, we just made 40 requests for every single character in our presumed character set. We can see that with A, we got like 18, 22 in terms of which one came back first, the A versus the star. Then we've got B, 20, 20, 18, 22. So these are all large numbers. But look at F. F came back 31 versus 9. This is a noticeable difference. Even though it's just that 1 nanosecond sleep, or presumably about a nanosecond, that should be about how long a context switch takes. Even though it was only that much, and that we're sending this over to a remote target, we can measure that difference because of this timeless timing attack. This is insane. This is absolutely amazing. Okay, so we can see that this F is 31 versus 9, whereas the rest, 19, 21, we can see that they're all about 50-50. Obviously, there's going to be some variance, as we said. One of the processes running might just context switch anyways, or who really knows? It's kind of, we're not given any guarantees in life on this. But we can do statistics to determine a pattern. And we can see very clearly looking at this data that F sticks out compared to everything else. Okay, and then so that took maybe 13 seconds. And then it looks like we're going for the next character. And look, again, we've got like 2020, 2317, but L, 35 to 5. This jumps out. Even though it's just that super small sleep, it is nevertheless to jump out. Okay, it's got FLA, FLAG, FLAG curly brace, T, TE, TES, TEST. Again, we can just see that even though it's that super small difference, that suddenly we're able to do timing attacks against a remote target. I hope everyone that has already gotten a chance to play this challenge enjoyed it. I hope you guys are able to learn a lot about about HTTP 2.0 and then also kind of this timeless timing attack. If you haven't, I would highly encourage anyone to actually read this paper. It's very interesting. They've kind of talked about a number of other things that this can be leveraged against. In my opinion, the most interesting, of course, is HTTP 2.0 because that is a huge attack surface. But there are, of course, other kind of domains that this can be applied to. So again, just keep reiterating, keep talking about how amazing this idea is. I've kind of discovered now that using this technique, because of the way that HTTP 2.0 allows us to multiplex requests over one TCP connection, that time variance no longer matters as it relates to the network. That basically, if you could have attacked a local host and measure the difference, you can do it now because the network variance no longer matters. Timeless timing attacks open up a whole new world into timing attacks against remote targets. This is amazing. Thank you very much.